Now, in this video, we are going to talk about electronics. In electronics, we've got three components. There is sensing devices, which we are going to call direct sensing. And then we have processing devices, where we'll be looking at the operational amplifier as an example. And then the third one, we'll be looking at output devices. So I'll make three videos separately, which I'll be explaining the three categories. So please watch the three videos so that you get a clear understanding of this topic of electronics. So without much further ado, let's start looking at sensing devices. That is the direct sensing part. Sensing devices can be used to detect many different types of change, e.g. changes in light intensity, temperature, strain, or magnetic field. The sensing device responds to external change by producing a change of PD because it is in a potential divider and its resistance changes, as in a thermistor, light-dependent resistor, or a strain gauge. In this case, we are going to be looking at the potential divider circuit itself so that you revisit it, because I know it's been covered in the IGCSE syllabus, but we are going to go over it again. Right, and then we also talk about the piezo-electric transducer as a sensing device. So in order that the information gathered by the sensing device may be communicated, it is going to be sent to a processing unit. So after the processing unit, an output device tells us whether the PD has been processed correctly or efficiently. So an example for a sensing device is an LDR, which is a light-dependent resistor, or a strain gauge. Then an example for a processing unit, like I said, the operational amplifier. And then the output device could be an indicator lamp or digital meter. So we start off by looking at the light-dependent resistor. So a light-dependent resistor is a resistor whose resistance varies with light intensity. So when there is light striking the resistor, you get an output. In other words, it allows current to flow through it. However, if it's in the dark, it won't allow current. There's very high resistance in the light. So very high resistance in the dark, and then low resistance in the light. The resistance of an LDR is constant at constant light intensity. These diagrams there that you see have to illustrate what I've just said, that when there's no light, the voltage does not pass through it. But when there's light, the voltage will pass through it. Now the graph of resistance against light intensity is going to be curvilinear, but then it's going to be in exponential decay, like this one shown here. Then I move on to talk about the thermistor. The resistance of a thermistor varies with temperature. So in the cold, the thermistor has a very high resistance, but in the light, it has got very low resistance. So we are going to be considering negative temperature coefficient thermistors. The symbol for a thermistor is as shown here. And you have the thermistor shown in real life. That's what it looks like. That's a rod thermistor. And then we've got a disc thermistor. And then we've got a bead thermistor. So you just connect them in the circuit by using these contacts. Again, the resistance against temperature graph is that of negative temperature. In other words, when the resistance is high, the temperature will be very low. So at low temperature, resistance is very high. At high temperature, resistance is very low. Then we talk about the piezo-electric transducer. The piezo-electric transducer looks like this, normally found in alarm watches. So this piezoelectric transducer converts variations in pressure, such as due to a sound wave, into variations in voltage. So now it's pressure against a voltage. Okay, so the higher the pressure, also we get a voltage that is high. So we deform it so that it produces it sends a signal. Okay. Quartz is a piezoelectric crystal made up of repeating silicate units. When unstressed, the centers of charge of the positive and negative ions in the lattice coincide. When the crystal is, however, compressed, the shape changes by a small amount and the centers of charge no longer coincide. A voltage is then generated across the crystal. This effect is known as the piezoelectric effect. We will talk about the piezoelectric effect when we will be looking at ultrasound. The polarity of the voltage depends on whether the crystal is compressed or expanded, i.e. whether the pressure applied is greater or less than the ambient pressure. The size of the voltage produced depends on the size of the pressure applied. Now, going back to sound waves, you know that they consist of compressions and rarefactions. When a sound wave is incident on a piezoelectric crystal, an alternating voltage is produced that varies in a similar way to the variations in pressure of the sound. To detect the voltages, opposite sides of the crystal are coated with metal and electric connections are made to them. The voltage produced can be amplified. The crystal and amplifier act as a simple microphone. Then we're going to talk about the strain gauge. Now, in a strain gauge, we are looking at deformation of the wire, whether we stretch it. If we stretch it, then there's a PD that is generated. So it is made by sealing a length of fine wire in a small rectangle thin plastic, as shown. So that's the plastic, and then we've got the wire in there. So when the plastic is stretched, there is a strain that is created. So in deforming the topic, deformation of solids, the AS topic, you know about Young modulus and stuff. So that's what causes, when there's a strain, then the PD is generated in this case. This causes the wire's length to increase and its cross-sectional area to decrease slightly. Both these changes cause the resistance of the wire to increase. Strain gauges are usually glued very securely to the material that is under test. So as you can see from here, that's the strain gauge. Now, when you subject this metal under stress, then the plastic also stretches and then sends a signal that is generated there. We know the expression for resistance is resistivity length over area. Now we're going to get a new length and a new cross-sectional area, which we then input, which gives us the resistance, the new resistance of the wire. Okay, so all this now tells us about the new resistance of the wire and the new length of the wire. So in this case, the area is assumed to be constant. We are going to assume the area to be constant, and then we get change in resistance proportional to the change in the length. Now, these are types of strain gauges that you can find. Then I'm going to talk about the potential divider, how it works. Now, our sensing device is placed right at the bottom there, and then that's where you get our output voltage. So we have an input voltage that is coming in, and then we have a resistor and our sensing device, and then the output. The cell or EMF of negligible internal resistance connected in series with the fixed resistor F and then the sensing device there. Now, this potential divider formula is arrived at when you consider the total resistance in the circuit. That will be F plus this R, which is our resistance of the sensing device. Now, to find the current that is flowing in the circuit, we say the EMF divided by the total resistance, which is I. Now to get the output voltage that then comes out from there, it will be the current flowing in the circuit that you've just calculated, E over F plus R, times the resistance there, R. So that's what you then end up with. V will be equal to that over that. Okay. The magnitude of the output voltage at any particular value of resistance R of the sensing device is dependent on the relative values of F and R. So in this case, if the resistance is large here, according to this one, you find that it gets a greater share of the EMF. So which means there will be more output PD. So the more the resistance there, the more the output voltage there, because R is on the numerator there. So it will get the lion's share of the EMF. So output voltage will be large. In this case, we do have a thermistor, so which means that in the cold, that's when it has very high resistance. So that's when you get a very high output voltage. And then when it is in hot, then you get the you get a low resistance there, and then that low resistance produces a low output PD. So in order for you to get a high output PD there, this has got to be in the code. So you can use this circuit, connect it to say a water bath, so that you produce a signal as long as the temperature is cold, so that it starts heating up the water. And then when the water is high, the temperature of the water is high enough, then this one will have a low value, so it cuts off, and then you maintain the temperature of the water bath. I hope that makes sense. Right, so I think I'm going to end here so that I keep my videos as short as possible. Please do comment, do share these videos on